Okay, hello everybody, and welcome to this week's video. Oh, I forgot to add a title to the OneNote page. Welcome to this week's video, in which we will be having a look at Noether's theorem. I think I'm saying that right. I'm not entirely sure. I did have a cheeky Google before I'm recording this. I understand it is Noether. I can't remember what nationality she is. Maybe I have it. Nope, I just have in 1915 mathematician Emmy Noether, which is unhelpful. Regardless. Um, well, let's begin. What is Noether's theorem? Well, this is 1915, so we are at the dawn of quantum mechanics. The dawn of, we're a bit into it by this point. But classical mechanics is still very much going on, and it's sort of the pinnacle of mathematicians trying to be cool and find as much out about, everything. And you have like Russell, I mean that's a bit earlier, which then leads into set theory and things like that, that are going on. And Noether is dealing with this view, which is we have a lot of conservation laws in classical mechanics that kind of like there's no theory that unifies all of those. You can calculate dEdt, or change of momentum as well, and then they always happen to be zero. But yeah, in 1915, Noether says, well, there must be something behind this, and she comes up with this statement, which is that every continuous global symmetry of an action corresponds to a conserved local current, which is what she says. So it's essentially this statement, well, it aims to explain why various quantities are conserved, and then she goes on to actually show it. We're going to look at the first theorem. We'll probably derive that for scalar fields, and then we will look at energy momentum tensor, and then we will look at U1 for charge. And that's what we're going to do. So let's begin. We're going to start off with the action. So let's take a set of scalar fields to the AX, where A is 1, 2, 3, to some big N. These are our field components. And we'll define this over Minkowski space-time. And then this is going to be governed by our fundamental action, which is S. This being a functional of phi, our scalar field, over some omega, any bounded region of space-time, and we'll have our Lagrangian taking in our scalar field, our muth derivative of our scalar field, d4x. Yeah, so this is our Lagrangian density. Sorry, I forgot to say that because obviously it doesn't take in and final parameter, and then this is just the shorthand for the derivative with respect to x, the x to the mu. Sorry, I'm deeply uncomfortable in my chair. I don't know why this is. It's not rolling onto my desk like it usually does. That's okay. So let's think about what exists at the moment. So if we have any arbitrary physical variation of our field, we can express it like this. I'm actually just gonna not write x anymore. plus some change in our field, right? That vanishes on this boundary d omega on our bounded region of Minkowski spacetime. And of course, if we now vary this with the principle of least action, we end up with the following very, very useful equation, which I'm sure you will all recognize, just in a slightly different form. Mu, and then we have, I'll write the bottom first, mu phi a, and you can see that this is just a nicely rearranged or a nicely changed for our conditions form of Euler-Lagrange. We say that any field condition that satisfies this is said to be on shell. I don't know why. It's probably got a reason, and I'm just being a thickie and cannot conjure it, but I'm sure there is one. So let's talk variations. We have to evaluate two types of symmetries. Those that transform space coordinates x to the mu, and those that transform our fields. So we have to be precise about how each one of these is measured. So let's look at each of them. Well, we're gonna have a transformation parameter epsilon, which you might remember from last week actually. I think I talked about Noether's theorem last week. I called it Noether's theorem, so sorry about that. Again, I didn't know how to pronounce it. We're gonna have a sorry, I forgot the dash as well earlier on. No, I didn't need a dash then. But I am going to use dash here. So this is our new position, which is x to the mu plus some minute change. And same thing for our phi, which is going to be phi dash a, which is phi a plus delta phi a. Now, what is this? Well, we can rearrange, and we can say that our delta phi a, or the minute change in our scalar fields, this is equivalent to the new position minus the old position. Let it be known that this takes x dash, whereas this takes x. So x dash, and that also takes x. And this takes x. This is going to be x, and this is also going to be an x. Okay. Well, this is interesting. We now have a way to compare our transformed field between 2 points. But we want to compute some derivatives, and we can't do that unless we compare fields evaluated at the same coordinates. So we're going to define an intrinsic variation, which is this delta bar phi a of x. And this is defined as equivalent to phi dash a of x minus phi a of x. And this is beneficial because all of a sudden now this delta bar insinuates that the phi dash function, the scalar field, takes into account the original position, not the new position. This is very important. Now we need to connect these in some way, so let's do that. Well, we'll start off by expanding our phi dash a that takes x dash. So phi dash a that takes parameter x dash, and this is going to be phi dash a x plus delta x, which is phi dash a x plus delta x to the mu, and then the muth derivative of phi dash a plus our O terms, delta x squared, which are of course very important, and I care so much about them. And I'm just going to leave that as epsilon squared for the future. Well, this leaves us then with phi dash a of x, which is this. Yes, plus. There is, to be honest, little. So just changing here, I believe. I'm just going to change it to O epsilon next to the mu derivative of phi dash. Oh, sorry, this then becomes phi a. Yeah, x plus O of epsilon squared. Nice. And this is our first order Taylor series. And now we can sub this back into our total variation definition. So if we take that, this minute change in our field x, this is phi dash a of x dash minus phi a of x, and we can see clearly that then this becomes phi dash a x minus phi a of x plus this thing, delta x to the mu, and then the mu derivative of phi a of x. Now this is great because we currently have a connection between, or rather we have something that just is taking an x. We don't have any x dash anymore. And so we can do something useful and extract the fact that this is notably our intrinsic variation up here. So now we have that this is delta bar phi a of, yeah, I'm not going to bother with because everything's an x now, plus delta x to the mu, and then the mu derivative of phi a. And we can rewrite this to be that delta bar phi a is equal to delta phi a minus delta x mu, and then the mu derivative of phi a. The derivative with respect to mu, not the mu derivative. I keep saying that. Now we can comment on this. Our intrinsic variation, this delta bar, evaluates changes at the same point. This then means that we can this function, so to speak, whatever it is, the intrinsic variation commutes with partial derivatives, which means that if we have delta bar of the derivative with respect to mu of phi to the a, this is the derivative with respect to mu of delta bar phi, the eighth a phi a. Now this property is incredibly crucial, as you'll see coming up, because it essentially allows you to define some symmetry for action. Let's look into that a bit more though. What does it mean for a transformation to be symmetric or be a symmetry? Well, we don't necessarily need the Lagrangian density to stay invariant. We only need our action to stay invariant, and of course those aren't perfectly equivalent. We can think about Gauss divergence theorem. The action here is going to be invariant if and only if the variation of our Lagrangian density changes by almost by at most like a pure total for divergence of some vector field, which is k to the mu. So we can write that. We can say that the change in our Lagrangian density, or total density, which is our Lagrangian, well no it's not, is the derivative with respect to mu of this vector field k to the mu. This is our full variation of Lagrangian density, which is including any stretching of our integration metric on d4x. Now we can do a coordinate shift, and I won't go and do the Jacobian stuff, but our coordinate shift is going to be x going to x plus delta x. And this leaves our d4 x dash being equal to 1 plus the derivative with respect to mu of delta x to the mu by our property. We can then be distributive momentarily. d4x, this is our new as in our neo metric. And so we can substitute this back in, and we have that the total change is going to be our absolute intrinsic change, delta bar of the Lagrangian, plus, and we can pull this out now, the derivative with respect to mu of the Lagrangian density times our delta x to the mu. This is wonderful. We now have a symmetry between our, or rather we can relate the change in our Lagrangian density overall to the intrinsic change of our Lagrangian density and the derivative of our Lagrangian density. And so now we can finally get to the bit where Noether did the thing, which is called the Noether's current, which, if we remember our statement from the beginning, which is that every continuous global symmetry of an action corresponds to a conserved local current, this is the current that Noether is talking about. So let's begin. The first thing we need to do is use our chain rule. I know. Well, chain rule, haven't heard of that for a while. We're going to find out what this is, our intrinsic change. This looks a bit too much like a music note for my liking, but I don't know how else to... Doesn't matter. Anyway, we need to find out delta bar of our Lagrangian density. And we can do that. We can then say that this is dl d phi a delta bar phi a plus dl d mu, that's not a d, sorry, d mu phi a delta bar of d mu phi a, and this is done by rearranging that and then using the chain rule on it, which is hopefully fairly self-explanatory. And we can now use our incredible commutation property to arrange some things. Notably, we are going to move this outside. So this is dl d phi a plus this is not, I'm not happy with this. There we go. Plus dl the derivative of the derivative with respect to mu of phi to the a times, now this is the key part, we are moving this partial out, and look what we have now. We have our well-defined intrinsic change in our scalar field, and we can apply product rule to this term to move things around in general, so that will shift some bits and bobs and it will actually be quite big. So we're going to work out what that is first of all, the whole term. So that is equal to, so we'll do this first. This is the same thing. So this is just, if you're familiar enough with calculus, you should actually just be able to see how all of these things are reformations of just standard calculus doodads. There's not really anything new here. It's just, it's like when you're presented with a new algebra, it's really just the same as all the other ones you've seen before. But instead of dy's and dx's, there's not many numbers in general, to be honest. There's actually not a single number here. That's vaguely harrowing. It's all right though. It all is meaning. And now we can substitute this back into our original expression, and I'm just going to group some terms in my head, because if I wrote it all out, it would be too large. So then our change in our Lagrange density, our intrinsic change, is going to be this L d phi A minus our derivative with respect to mu of. I'm going to have nightmares of this after. I mean, I did these notes earlier, um of this stupid derivative. That, and then phi of A plus our, sorry, I can't when it looks like a 5, plus our derivative with respect to mu of that same phi to the mu, no, to the A, and then it's dl, and then again, this is wholly algebraic, but if you were to break it down, you can think about what everything means, and at the moment, there's no specific meaning to each step. It's more to do with the fact that we're trying to get this into a form that we can do something with, and we actually have got this into a form we can do something with. If you look at this expression that I've helpfully labelled in square brackets for you, you may see some semblance to something I brought up right at the beginning, which was the Euler-Lagrange equation for this setup for our Lagrangian density and our Minkowski space, with respect to our scalar fields. And that's that. Well, that's pretty useful, isn't it? So we can rewrite this, or rather we can substitute our equation from earlier, which was this one we came up with up here, the one after that, this one. This is really useful. We can substitute that back in now. Or rather, we can substitute this into there, which is going to leave us with the following. I am just going to write EL because I'm not doing all of that again. You've got it up there, you don't need it again. So now this is our total change in our Lagrangian density, and we're just subbing back into that formula. So we've got Euler-Lagrange, phi so A plus this mu dl, that's not 1, d sub mu phi to the A, and then we have this appended term, which is our mu, the derivative with respect to mu of our Lagrangian times by our change in position, which we have from the ends of our equation up here, which is not there. Where did I put it? I thought this didn't look right. No, that is right. Yeah, sorry, I'm blind, obviously. Wonderful. This is grand. But we can do things to simplify this further. For example, well, we have a nice derivative with respect to mu that we can combine all of that stuff, and then we can actually pull that over to one side. And what we will see now is something very, very interesting. Also, we can look at our symmetry postulate, which is this with our vector field there, and our mu derivative with respect to mu of that vector field. Well, let's see what we get. We're going to have this d mu k to the mu is equal to EL Euler-Lagrange plus this derivative with respect to mu of dl over d mu phi a d phi a plus l dx to the mu. Great. This is beautiful. Because we can rearrange and pull spatial derivatives onto one side, which is going to pull that inside of there, and then what we will end up with, moving that to the other side, is the following, which is that the derivative with respect to mu of all of those things together, so the derivative with respect to mu of our scalar fields times this absolute times our intrinsic change in eigenchange. Oh, I like that. In our scalar field times this Lagrangian density function, which is plus our Lagrange density function times our change in x, plus or minus actually our our arbitrary, it's not arbitrary either, I'm struggling to come up with the word, our vector field that we defined earlier is equal to minus the Euler-Lagrange that we defined before times the change, intrinsic change in our scalar field. Now. You may remember earlier when I made a strange remark about on shell, and you may be thinking, well, that's a bit of a useless bit of trivia, it's not going to ever come up. Well, it is, because if we enforce that our equations of motion are all satisfied, this is the condition of the system being on shell, then, well, this is going to be zero, isn't it? Because Euler-Lagrange, and Euler-Lagrange is zero, that's how it works, that's how it's defined. So that goes away. That whole thing goes away, actually. So Shell, not the terrible oil company, thank goodness. Might send a hitman to my house for saying that. Sorry, Shell. That is zero. And so now we can define the quantity inside of this derivative as something called the Noether current, which Noether defines as J to the mu, as currents often are for some reason. J for current, I'm sure it comes from something. The derivative with respect to mu of phi to the a of our Lagrangian density times the intrinsic change in my scalar field plus the Lagrangian times the change in x to the mu, the position, minus our vector field. And this is it's actually equivalent. It should be equivalency. Remember, Noether was a mathematician, fairly rigorous. And now I can stop writing all of this stuff out because I've defined it. And now, so this leads us to, if we're working with an on-shell system, we have a beautiful conservation law, which is simply that the derivative of the Noether current with respect to mu is simply equal to zero. Isn't that glorious? Isn't that truly, truly beautiful? I think so. I think it's fairly useful. Or, as it is also defined, the derivative with respect to time of J naught plus the divergence of the other terms is equal to zero. And we can get something also useful. We're working with a current, and everything in science, especially physics, likes to mirror itself. So if we have a current, we can probably integrate and then find a charge. and we can integrate over space here, so we do q. This is our Noether charge, which is the integral d cubed x j to the naught, and so we have that the change in charge with respect to time is equal to 0. Well, that's a useful one, so we have conservation of charge. This is really algebra heavy, and it looks scary, and it can feel like that. But I hope I explained it to the extent that you're able to follow, because really, it is groups of symbols together that have meaning, and the operators between them that have meaning, rather than specific things. And really, what we've done here, if we just let the algebra lead us to this being equal to 0, then we can clear that up and deal with it later. So let's do something with it. Namely, we'll look at the stress energy tensor. I think we can, get through all this stuff. That's fine. So, let's apply this to some translational symmetry. So now I'm gonna wiggle, and we're gonna have a position x mu, and this gets transformed to x dash mu, which is x mu plus some epsilon mu, where epsilon is some constant infinitesimal full vector. And this is a pure coordinate shift, so these scalar field values are going to be unchanged at the shifted point, which of course can be written as the change in the scalar field being moved to 0. And so now we have an equation for the intrinsic change, which is minus epsilon to the nu d nu that's alright. Sorry. I was really enticed in how on earth you draw a nu properly. That's alright. And then the derivative with respect to nu of our scalar field. Obviously, because this is equal to 0, we can get rid of that term. Now, the total variation of the scalar Lagrangian under this coordinate shift is just a directional derivative. So we can plug that in, and you work through, and you then find out that this vector field k is epsilon epsilon to the mu times that Lagrangian density function. And we can put this then into our current definition of the density, which is this, and what it ends up becoming is minus epsilon to the nu of essentially what we had before, but we've lost our term relating to this because it's gone to 0. d nu phi a minus, and now I have this eta term, which is simply, I will show you now. What it is. What you end up with is this thing in the algebra, which is Lagrangian times epsilon to the mu minus epsilon to the mu times the Lagrangian, and what we can't have here is, because they're not necessarily commutative, we can't have these to cancel, and so what we're left with is this eta term to the mu and to the nu. But we can, I'm not too bothered about this. It's just mathematical formalities. Well, if we now, well, we have factored this out, and now what we have is something that's quite useful, which is our canonical stress energy tensor. We can get rid of it basically because it's just some arbitrary parameter. So now we have stress energy tensor mu and nu are the indices, and this is sub mu phi a. That's on a. There we go. The L mu phi a minus that from before. This is our stress energy tensor. I forgot to get rid of that's lackluster. Sorry. This is our stress energy tensor, which is quite an important one. I've definitely used this in quite a few videos. And of course, since these are pretty much the same thing with a couple of changes, we can sub this back into there and see that the derivative with respect to mu of the canonical stress energy tensor is 0, and thus stress energy is conserved, energy is conserved, many things are conserved. That's quite wonderful, to be honest. So yeah, we can look as well at how this leads to the Hamiltonian. Well, the Hamiltonian is our integral d cubed x of our indices naught stress energy tensor, which is d cubed x d Lagrange d. I probably should have started using dots quite a while ago. That would have made things a lot easier, but it's important to be specific here. This as being 0, 0 is going to go away, and so we end up with this being the Hamiltonian or total energy of our field, which is grand. So this is our conserved charge here again, coming back. Now the final thing I want to look at is how charge is definitely, electromagnetic charge is conserved. And we can look at it. I will do a final squiggle. Squiggle, 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 squiggle. We're gonna take I'm gonna define a scalar field. It's this one. It's going to be 1 over root 2 times phi 1 plus I phi 2. And this is governed by Lagrangian, which is the muth derivative of all of our scalar fields times the derivative with respect to mu of our scalar field minus m squared phi star phi. And this is this star being our derivative here. This, of course, is a Lagrangian of that. If you were to consider the energies, the maximums and the minimums, this is what we get. Now, let's look at U1. U1 being U1, which I would have talked about in previous videos relating to group theory. What we're going to do, this is unitary group 1, is test an internal global phase transformation inside of U1. So we'll rotate the phase of our field by some angle alpha. So we're going to have this translation to phi dash, which is going to be e to the I alpha times our phi, which is our little rotation, and this is roughly 1 plus I alpha phi, which is phi plus I alpha phi. We can compare this to our original field and actually plug this in to things momentarily, but I just want to touch on the fact that our space-time coordinates here are not touched at all. So delta x to the mu is 0 and k to the mu is 0, which means that our delta phi and our delta bar phi, our intrinsic change, are just going to be I alpha phi. And we have our conjugates, which are here. These are our conjugates with the stars. That's what that means. Our delta bar phi star being minus I alpha phi star. Let's plug this into the Noether current. Well, shows the mu is equal to dl d sub mu phi delta phi plus dl d mu times our conjugate of phi times the intrinsic change in that conjugate. And I will not bore you with more. I'm sure 41 minutes in, you're probably not that interested in watching all of the steps. I will leave it to anyone who's brave enough to make it this far through the video to do it themselves. But it's not particularly hard, to be honest. You end up with this just literally by plugging things in that have been stated previously. There's no anything trickery here. But what's important is we can now get rid of this scale factor alpha. And so we actually get a j of mu in conserved in U1. And this is our electromagnetic current density. This is I times our conjugate of phi d mu of phi minus phi, oh, hello, minus phi times the derivative with respect to mu of our conjugate of phi. Brilliant. And if we take this to be an on-shell system, this still satisfies our equation for the muth derivative of our current being equal to 0. Therefore, Q is conserved, dq dt is equal to 0. And so after quite a bit of stuffs, we have shown that, Noether had a theorem, came up with the Noether current, which is this, noted that for an on-shell system this Noether current is equal to 0, the derivative of this is equal to 0, and thus it is conserved, and shows that you can derive the quantities that are conserved in all of classical mechanics using this single formula, which is pretty incredible if you think about it. And it proved that space-time is homogeneous, and it proved the statement that Noether claims at the beginning, which is that every continuous global symmetry of an action corresponds to a local current. And these are our local currents. This formula is our local current. Well, I'm going to go and scroll up here for a nice thumbnail. But, yeah. I hope you enjoyed this video. I was always a bit nervous about tackling Noether's theorem because it's notoriously hard. It's really mathsy. But I hope it's been alright. And yeah, I hope you've enjoyed this video. And yeah, I'll see you next week. I'm not sure what we'll be doing. Possibly something I had in mind. Deriving the Feynman path integral? Sounds fun. But we'll see. Anyway, have a very nice week, and I'll see you then. Goodbye.